Right, in this lesson we're looking at section 2.5, polynomial functions. And the objective for this lesson is to be able to find the zeros, or as we've already discussed, the x-intercepts, or even solutions, all of those words meaning the same thing, of any given polynomial. We've done this with factoring in problems in the past, and those problems were actually fairly basic. It's the problems that don't factor that are more complicated. And that's what we're dealing with here. So for example, in example 1, we're looking at 4x cubed plus 2x squared minus 5x plus minus 3. This function will not factor in any simple way. It may have easy integer or even rational answers, but we aren't going to be able to find those easily through factoring. And since it's a cubic function, we can't use a quadratic formula. So we need another method. That's where the rational zero theorem comes in. So the rational zero theorem, I won't go through this entire bracket or theorem in the way it's written because it can be quite confusing, but basically it says that if there are any zeros for the polynomial that are rational numbers, then they will be among the list that can be created with the constant term and the leading coefficient. So what we have to do is find the factors, that is, the numbers that are multiplied to give us the constant term, and divide those by the factors that are multiplied to give the leading coefficient. So in our first example, the constant term is this term on the end, the -3. Notice I'm matching the colors here. And then the leading coefficient term is the 4 right here. So the example says list all the possible rational, or all the possible zeros of this function. It really probably should have said list all the possible rational zeros. And I'm going to note that here because there could be irrational zeros in the polynomial, and they will not be among this list. For those of you who have forgotten, a rational number is a number that can be written as a fraction, and an irrational number is something that can't be written as a fraction. For instance, an irrational would be something like pi or square root 3, etc. All right, a rational number, 1/2, 5/3, whatever. Okay, so if we're listing all the possible rational zeros, we're going to list this as the variables they use are p divided by q. And so we take the factors of the constant term. The constant term is 3, so all of the factors of the constant term are 1 and 3, positive and negative, because if I multiply -1 times +3, I'm going to get -3. If I multiply +1 times -3, I'm going to get -3. All right? And for the leading coefficient, the factors are 1, 2, and 4. Since the number's 4, the only numbers that go into it are 1, 2, and 4. So among this fraction, if we break it down, we can get 1 over 1, which of course is 1, 1 over 2, or 1 over 4, but we can also get 3 over 1, which is 3, 3 over 2, or 3 over 4. All right, so it's not enough just to leave it in this fraction form here. We need to break it down into all the possible individual values. I'll let you just write the plus minus one time in the front of it rather than writing it on every single number, but technically it should be on every number. And so what we have here is a list of 12 different possible values. There are 6 unique numbers, 1, 1/2, 1/4, 3, 3/2, 3/4, but since it's positive and negative, we have 12 possible answers. So what are we saying here? Essentially, if there is any rational zero to this polynomial, if there are x-intercepts or solutions or zeros, then they will be, if they're rational, they will be in this list. And that's all we know. All right, so if we can create a list like this, we can then narrow down from what is an infinite possibilities for x-intercepts. We can narrow it down to a list of, well, in this case, 12. So it's pretty significant, but still a big number. All right, let's move on. Example 2 says find all zeros. So don't just list them, find them all. So to begin, we will start by listing what the possible values could be. So we're going to do our p over q again. So in this problem, our leading coefficient is 1, but our constant term over here is 20. So we're going to get the factors of the constant term, plus minus 1, 2, 4, 5, 10, and 20. Those are all the numbers that go into 20. And then, of course, that's all divided by plus and minus 1. And so essentially, we just have 1, 2, 4, 5, 10, and 20. We don't have to divide them all by 1. So that is, again, 12 possible answers. All right, so the question is where to go from here. We've got all these possible zeros. We could sit here and plug every single number individually into the function for x and see if we get 0 as an answer. And that would be kind of annoying. Or we can be a little more careful about it. If we remember what we did in the last section, section 4, we said if we do synthetic division with any number and we get a 0 in our remainder, then that means that that value is part of the factored form of that polynomial. In other words, it means that that number is a 0 of the polynomial. So out of this list of 12, we're going to test numbers until we get one that has a 0 as the remainder. So it is still a lot. It's 12 values. We can choose any one of the 12. I'm just going to go with 1 first. So if I put 1 into this polynomial, the coefficients are going to make up the next line. They are 1, 8, 11, and negative 20. Make sure you take the sign with it. It's positive 1, positive 8, positive 11, and a negative 20. Remember from the last section, we're going to drop down the 1. We're adding vertically, right? Drop down the 1. Multiply, we get 1. Add, we get 9. Multiply, we get 9. Add, we get 20. And here we go. Multiply, you get positive 20. Add, you get 0. So we got a 0 in our remainder, which means 1 must be one of our answers. I'll go ahead and start creating that list now. If I want all the zeros, I know that 1 is one of them. If 1 is a 0, then that means the factor x minus 1 goes into our polynomial evenly, and when we divide x minus 1 into the polynomial, we'd be left with, these are our coefficients, we would be left with x squared plus 9x plus 20. And we're kind of home free from here. If we're trying to figure out where this polynomial equals 0, and please understand, this polynomial is just a factored version of that polynomial. It is a factored version of our original question. We've broken it down into a linear factor times a quadratic factor instead of just a cubic polynomial. But if we get a quadratic, we can use the quadratic formula from here. Or, if we're lucky, it'll factor from here. And this one actually does factor. So x squared plus 9x plus 20 will factor into x plus 4 and x plus 5. Which is to say that if we had tried negative 4 in our synthetic division, or if we had tried positive 5 in our synthetic division, then we would have also gotten a remainder of 0 in synthetic division. All right, so we've just found that negative 4 and positive 5, negative 5. Negative 4 and negative 5 are also zeros. And that is, it's a cubic polynomial. That's all 3 answers. All right. Let's try another one. Example 3. Find all zeros. Same question. All zeros. So we can do a quick look at the function and see that it's not going to factor neatly, and that's because the only factoring strategy here would be grouping. I could take out x squared, which would give me x plus 1, but there's nothing I can take out of this that's going to give me an x plus 1. So factoring is futile. Let's not do it. So we can go p over q. We get plus or minus. The factors of my constant term, luckily, are just 1 and 2, and the factors of the leading coefficient are just 1. So all we have here are really 4 possible answers, and that's nice. With 4 answers, we can just jump straight to plugging them in and maybe we get lucky. Let's try 1 again. If I plug 1 in, remember my coefficients are what I need here, so 1, 1, -5, -2. Take the sign with it, and if you're missing a term, put a 0 in its place. We're not missing a term in this problem, so we're good. So I carry down the 1, I multiply, I get 1, I add, I get 2, multiply, I get 2, I add, I get -3, multiply, I get -3, and add, and I get -5. That doesn't work. I've got a -5 in the remainder position here, so I'm going to trash this work. 1 is not one of my zeros. And I'm going to try again. This time, let's move on to 2. If I use 2, same coefficients, 1, 1, -5, and -2, then we get, bring down the 1, multiply, I get 2, add, I go 3, multiply, I'm going to get 6, add, and I get +1, multiply, and I get +2, and I add, and I get 0. Bingo, that's what I needed. So we've confirmed that from our original statement, again, this is the original, we can factor into x minus 2, right? If this number leaves you with a 0 as a remainder, then that means x minus 2 in this case, or that number being subtracted from x, is a linear factor. And we're left with the coefficients x squared plus 3x plus 1. And we have quadratic, and that quadratic is usually easily solved for when we try to set this thing equal to 0. All right. Unfortunately, if you try to factor this one, it's not going to work. So we got to go to another strategy. And our best option is quadratic formula. So x equals -b plus minus square root b squared minus 4ac all over 2a. If I plug in here, -b, again, I'm only interested in the one I've got underlined here in red. I'm only interested in this one. I'll highlight it now. I don't need to mess with the other factor. I know that x equals 2 is already one of my answers. +2 is an answer. All right, but I'm trying to find the others. Quadratic formula gives me -3 plus minus square root of 3 squared is 9 minus 4 times 1 times 1 all over what is 2 times 1. So I've got -3 plus minus the square root. It looks like 9 minus 4 is just 5, and it's all over 2. -3 plus square root 5 over 2, and -3 minus square root 5 over 2. Those are my other two answers. You could put it in a calculator and get a decimal, but my math lab is not going to accept that. Instead, my math lab will require you to write out each of these individually. You're going to have to give the -3 plus and the -3 minus as its own answer. And there we have it. I know I went with multiple colors there, but 2 is our first root, and then these other two are irrational. So you'll notice that our function was originally a cubic function. We got 3 answers, right? 1, 2, 3. But only one of them was in our list that we created at the beginning. And that is because the list only gives you rational zeros, possible rational zeros. The fact is, they're only a possible rational zero. There's no guarantee that any of them work. Obviously, we'll set you up with polynomials that generally one of them at least will work. So we got one of them to work, and then the other 2 zeros were irrational, and so therefore they didn't show up in our list. All right, moving on. Find all zeros. Here we are with a 4th degree polynomial, so this one's going to give us 4 answers in the end. And it's not going to factor, so we're going to jump straight in with our list. P over Q. We get positive and negative. The factors of the of the constant term divided by the leading coefficient. The constant term is 1 and 13. It's prime, so we lucked out. Only prime numbers, so it's going to be simple. And then we're going to divide by 1, which means I don't really need to write it. We just have positive -1 and positive -13. So we have 4 possibilities. So let's jump in. I started with 1 for all the other ones, so let's start with 1 here. If I plug 1 in, where I try to divide by 1, then my coefficients are 1, -6, 22, -30, and +13. All right, notice I go 4, 3, 2, 1, and then this is x to the 0. That's a 1 right there. So I do not need to put a 0 in place of anything. I have it going down in perfect descending order from 4 down to 0. All right, carry down to 1. Multiply. I'm going to add, I get -5. I multiply, I get -5 again. If I add here, I'm going to get 17. Multiply 17. If I add here, I get -13. If I multiply, I get -13. And bingo, we got 0 in the end. So perfect. What we're saying here now is our original f of x statement can be broken down into the factor x minus 1, again extracted directly from this, x minus 1, times my coefficients give me x cubed. Remember, we started with an x to the 4th, so the next one's going to be x cubed. X cubed minus 5x squared plus 17x minus 13. And unfortunately, unlike example 3 or example 2, where once we were done with the first one, we had a quadratic left over, this one we have a cubic function left over. And that cubic function cannot be factored easily. It doesn't factor, in fact. So, or doesn't factor in any methods that we have. And so we are stuck basically repeating the same process one more time. Now here's the catch. Listen carefully. Any of the possible rational zeros that we listed at the beginning, that list that I just circled is still the comprehensive list of all possible rational zeros in this polynomial. So if there are possible rational zeros, they're going to be in this list. There's only 4 options. There are only 4 options. So if I tried this again to create a list, a new P over Q gives me basically the same thing. If you look at it, it gives me positive -1, positive -13. Unfortunately, that list doesn't get me anywhere. It's right back where I started. But for this polynomial, this list, 1 and 13, are the only possible roots, which means 1 could be another root. It could be a double root. It could count as multiplicity 2. All right? I would not, if I were doing this problem, I would not generally write this. I'm going to erase it. I would not generally write that list again. I would go back to the original list. Go back to what I just circled there. We don't have to write it twice. All of the possible rational zeros were in our original list. So let's try it again. The key to this problem, though, is that you realize that we could have a repetitive root. And if I try any other number, I'm going to find it doesn't work. And I only know that because I've done this problem multiple times. So, in other words, what I'm saying is we're going to try 1 again. Don't be afraid to try a number more than once if what you're left with could possibly use that 1 again. Okay? Here we go. So I'm putting 1 in, but this time my coefficients are 1, -5, 17, and -13. So I'm going to go off the smaller polynomial that I've created. Drop down the 1, multiply, I get 1. Add, I get -4. Multiply, I'm going to get -4. Add, I get positive 13. Multiply, I get positive 13. Add, I get 0. And bingo, we've done it again. We have another factor of x minus 1. So we have the original x minus 1. We've got another x minus 1. And then we're left with x squared minus 4x plus 13. So we have taken what was a quartic, a 4th degree polynomial, and we have broken it down into a linear times a quadratic. And once we have it in that quadratic form, we're home free, because we can jump straight to the quadratic formula to solve for the remaining zeros that we need. I'll point out, by the way, that I could write this x minus 1 squared times x squared minus 4x plus 13. And then it's easier to see that that is a double root because of the square. All right? So I'm going to use quadratic formula here on this quadratic that we have left over. So x equals the negative of negative 4 is positive 4, plus minus the square root of negative 4 squared is 16, minus 4 times 1 times 13. And if you are somebody who likes to think ahead, you're already noticing that we have an issue with this radical. We're going to end up with a negative inside. All right? We get 4 plus minus square root of, it's 16 minus 4 times 13 is, well, 4 times 10 is 40, 4 times 3 is 12, so it's 52. Negative 52 and positive 16 makes negative 36 all over 2, which gives us 4 plus minus 6i over 2, which gives us 2 plus minus 3i. And notice that is two different answers. It's 2 plus 3i and 2 minus 3i. And if you combine those two with the double root we had earlier, we have all 4 solutions here. Our answers are 1, I'm only going to write it once, even though it counts twice, and then 2 plus 3i and 2 minus 3i. That's how you'd have to write it in my math lab. All right, this, I would accept, by the way, if you were giving this as an answer on a test, I would accept 2 plus minus 3i. You would not have to write it individually, but on my math lab, it's going to make you write it individually. All right, so there we go. We found all 4 of them. A little bit odd. Again, the catch here, the tricky parts where we had to use the 1 twice. That's really unusual, actually. It doesn't happen often, but it happens. And I wanted to put this example on here so you knew that not to be afraid of it. Don't be afraid to use a number more than 1 time if you still have to go further with that polynomial. And then second, we had imaginary numbers. All right. And then finally, our last question says, find a 3rd degree polynomial. That means find a polynomial whose highest power is x to the 3rd with real coefficients, so that's not unusual. All polynomials should have real coefficients. That has negative 3 and positive I as zeros, as x-intercepts. And then they give us this other weird piece of information here. F of 1 equals 8. Again, not quite sure what that is yet, right? But technically, all they've told us is that when x is 1, the function will equal 8, or y is 8. So they're giving us a point on the graph, really. They've given us this individual point on the graph. All right? I didn't go over the theorem that's written right above it, but we have talked about it if you read this one exactly. The fundamental theorem of algebra, we've talked about this. I've mentioned it in class before. This is the first time we've actually had it in writing. But it basically says that if you've got a polynomial with degree n, if your degree is n, then you're going to have n real zeros. This says has at least 1 complex root. Well, that's not really saying much because all of our roots are complex. But you'll have n real, or sorry, not real, n zeros, n solutions. All right? So they've only given me, we're supposed to come up with a 3rd degree polynomial, but they've only given me 2 solutions. They've given me negative 3, and they've given me I. Well, the key here, though, is that you realize that complex imaginary roots, or zeros, always come in conjugate pairs. Oop, I just spelled conjugate wrong. Conjugate pairs. They will never come alone. So if they tell you I is a root, then we have to have the conjugate of it, which is negative I, right? Conjugate pairs, again, if I have a plus bi, then I have a minus bi as a root. Well, we don't have an a, this is given to us as technically I, which means it's 0 plus 1I. And then the pair would be 0 minus 1I. So if I is a root, negative I is a root. That's all we've been told. So technically we have all three roots, or all three zeros. I keep using that word root, but earlier in the problem they used the word 0. All right? All right, so we've got all of them. I'm going to start building my polynomial here. My voice is going out. I'm tired. So f of x equals what? I know it equals x plus 3. That's extracted from this negative 3 over here. If negative 3 is a root, then x plus 3 must have been the factor. And then I also have x minus I and x plus I. Now notice I left a little space in the front. Because here's the deal. There's always the possibility of a number in front of my polynomial. I'm going to call that number a. But that number could be anything. It could be 3, could be negative 7, could be anything. Let me just give a quick example. If I had, let's say, y equals 2x to the third plus 6x squared minus 10x plus 4, then I could factor that and pull out a 2 before I do anything else. And then maybe what's left factors further. But what I do know is that this 2 out in front would not show up if I was listing the roots. And that's what they've done for us. They've listed the roots, but we don't know if there's a possible number stuck out in front, like this example I've written. All right? So we have to put this a in here to represent the possibility of a factor in front. I will tell you that I remember most of my math lab questions, that a value is just expected to be 1. And so you don't even have to worry about it. The only time you have to worry about it is if they give you another piece of information. That other piece of information here is this. They told us that f of 1 equals 8. So in other words, we're going to be able to find that a value based on that point. All right, more on that in a moment. For now, let's just leave it alone. All right, they wanted us to build the third degree polynomial. So far, we have not done that. All we've done is just kind of written out the factored form, and we haven't found the a value. So we need to do it. I'm going to start out by multiplying these I terms. All right, we know that when we multiply two conjugate pairs, we end up with the square of the first term, which is x squared, plus the square of the second term. Well, actually, it's going to end up being minus the square of the second term, but it'll be plus in a moment. So minus I squared. All right, we're going to get a squared minus b squared, basically, in the difference of two squares scenario. But since it's I squared, that's going to turn into plus 1. Right? It's minus I squared, and we know that I squared is equal to negative 1, so it's going to turn into plus 1. Okay, so we've got a times x plus 3 times x squared plus 1. That's what we're looking at. I'm going to keep that a as a red number just to make sure you recognize it's sitting outside. We still have to deal with it, but we'll get to it in a moment. All right, before we get to it, let's go ahead and multiply. Oh, I keep meaning to write that in red, sorry. If we multiply these two factors, we're going to get x cubed plus 3x squared plus x plus 3. And it's written in descending order. I kind of went out of order in our FOIL, but still. So f of x is equal to that. All right, well, great. I also know that when x is 1, f of x is 8. So if I put 1 in place of all the x's and I put 8 in place of I put 8 in place of f of x, put a 1 here, a 1 here, and a 1 here, I'm going to be able to find a. All In fact, I'm going to get 8 is equal to a times 1 cubed is 1, plus 3 times 1 squared is 3, plus 1 plus 3, that's 4 plus 4, which is 8. So a, after all that work, turns out to be 1 anyway. I'm going to divide by 8, right? And I get a equals 1. So ultimately, my final answer here, I'll write this in green. Green means go. After all that work trying to find a, it turned out that a was just 1 to begin with. That's kind of annoying, but oh well. This is my answer. X cubed plus 3x squared plus x plus 3. I now have a third degree polynomial whose roots are -3 and positive I and negative I. All right, that'll do it. That concludes this video. I hope you learned something. Feel free to watch it as many times as you want.